All right, so far we've looked at the average rate, that's just a change in concentration of the change in time. We've looked at the instantaneous rate, which is the rate law stuff, so that's saying if the concentrations are this, the rate at that point in time is going to be this. The problem with both of those, though, is with the average rate, we just get kind of the general rate for the entire reaction, and so it doesn't take into the account that the fact that it's starting out really quick and then slowing down as time goes on. The problem with the rate law equation is that it doesn't take into account what the concentration is going to be after it's started. So let's start out by talking about first order reactions. So the rate for a first order reaction, and let's just assume it's a general equation of A turning into B. So with the first order reaction, we have a single compound that's doing all of the reacting, so that's all that we're concerned about. If there is anything else that's reacting, it'd be zero order, but the only things that are in there are going to be that single product, so it would be the reaction constant, rate constant, times the concentration of A raised to the first power. That would make it first order. So when we look at this right here, what we're saying is the rate for this given concentration. But think about it, the moment this reaction starts, the moment that A starts reacting, it's turning into B, its concentration is going to decrease, and the rate's going to change. So this particular rate for this particular concentration is an instantaneous rate. It only happens for a fraction of the time. Okay? Once it starts reacting, that concentration goes down, the rate changes. And the average rate that we talked about before is just the change in concentration of A divided by the change in time. And of course that's negative since A is disappearing. So when we look at a graph like this, we can see that the curve goes down, but we're not always blessed with such a nice little pretty graph to show us what's going on over time. Sometimes we need to be able to calculate what the rate is or what the concentration is based upon time. So if we look at this equation right here, we want to find a way to relate the change in time to the concentration. So when we have a graph like this, well, we can find each plot along the way, but if we don't have a graph, it's going to be really tricky to find what the concentration is at this point or at this point without a graph to do an X and a Y grid. So if we bust out with a little bit of calculus and we integrate the first order reaction, so if we take this information right here and we integrate that, don't worry about integrating because many of you aren't in calculus yet or probably haven't talked about integration. But if we take a look right here at this graph, we can see an integrated version of this rate law right here. So what we do is if we take the natural log of the concentration and we put it with a graph against time, we see that now we get a nice linear plot. So with a linear plot like this, it's a lot easier to find the concentration at any given point along the way. Not just along the dots that we've already calculated, but any space in between there. And what's great about this is once you do that, you're going to find that the K, so that rate constant, is also the slope, the negative of the slope. And slope is just rise over run. And so if we can find the slope of that, we can find the rate constant. So here we see that same equation again. The rate is equal to the change in concentration over the change in time, which is also equal to the rate law, which is the rate constant times the concentration of A. So we can integrate that, and we can get this equation right here once it is integrated. So this is the calculus thing. The step to go from this point to this point is something that you would do in calculus. So we're not concerned with that. Here is the final product right there, and this is what you need to know. So this equation is given to you on the equation sheet. However, it is not labeled as the first order integrated rate law. This equation only applies to a first order reaction, for a reaction that's overall order is first. You need to recognize this equation as the one that applies to first order. There's a different integrated rate law for the second order reactions. It's also given to you, but you need to know which goes with which type of reaction. So what we're saying with the integrated rate law is the natural log of the concentration at time t minus the natural log of the concentration at time 0 is equal to the rate constant times time, the negative of that. So here's what this means. Concentration at time t, that would be the same t as right here. So let's say the reaction goes on for 5 seconds. We would take the concentration at time t, the natural log of it, so after 5 seconds the concentration, and subtract it from the concentration at time 0, so what it started out as. So, for example, let's say you have 5 molar of A. All right, and you start it reacting, then you go and you make yourself a sandwich, maybe take a shower, you come back 10 minutes later, and you say to yourself, I wonder what the concentration of A is now. So you look and you say, all right, so I started with 5 molar, 10 minutes has passed, we know the rate constant, and so then we can calculate what the concentration would be at 10 minutes. So the rate constant times 10 minutes, and then you just have your initial concentration of 5 molar, and you find your concentration at the time. Prepare to have your world rocked. So all those things you did with graphing and Algebra 1 or whenever you did it, and you learned about straight lines or linear equations, they're now going to have an application. What I'm about to show you is very important for any laboratory science. Any quantitative chemistry class or any quantitative science class that you ever take, you will use this concept right here. So we take a look at the first order integrated rate law. Let's say we want a way to figure out what the concentration is at time t. So that whole problem where you go and you take a shower and you come back and you want to figure out how much you have left. If we rewrite this equation, so the natural log of the concentration of A at time t, and we would be able to figure out really easily what's our concentration at this time. It would be equal to the negative kT plus the natural log of the concentration of A naught at time 0. All right, that's just this order, this equation rearranged in a different order. So now we can plug in the numbers right here. Okay, the concentration initially would always stay the same, and we just change the time in that number right there. Just change the time. We can figure out what the concentration is at any given point in time. But here's the cool thing. If we look at this equation, and we think back to that slide that showed it as a straight line. Straight lines can be solved for with the equation y equals m times x plus b. This is a beautiful thing because if we line this up, we see that the y value would be our natural log at time. We would see that our slope, the m, would be the negative k. So I'm going to go ahead and put that negative k in parentheses just so we can keep it separated. That would be our m. Our x value would be time, and our y-intercept would be our initial concentration. So this means that we can plot our data and we can find out what the concentration is at any given point in time without having to do any new integrations, without having to do any new order calculations. We can figure it out just by looking at the graph and its slope. If that does not amaze you, then you are not capable of emotions. Here's how this would work in a laboratory. So you'd make a graph, and we would take the concentration of A, the natural log of it, and then plot it against time. And so the chemist, a scientist, would do 3 or 4 or 5 different experiments. And so they would take a concentration, and they would take a reaction, and they'll always start with the same amount. So let's say we always started with this amount. And then after a certain amount of time, we'd find out what the concentration is, and well, it would be right there. And then we would do it again and find another concentration after time is going on. We would find it right there. And then we would do it, let's do it a 4th time. We'd find it right there. So we would just find 4 data plots, plot them, and we would get this line on our graph that would end up being straight. So then when we would find that, we could use data to do it or just rise over run, and then we could find the slope of this line right here. And the slope, we have already found that the slope is the k. So once you find the slope of that line, you're going to know what your rate constant is for that particular reaction at that particular temperature. What this means is once we have this slope, once we have this straight line, we can use this equation to figure out what the concentration is at any given point in time. Even though we only found the concentration here, here, and here, we can, with simple math, figure out what the concentration was right there, right there, right there, without having to do any more data collection. We've just collected 3 data points, and now we're able to find an infinitesimal amount of different concentrations. We can figure out what the concentration is at any given point in time, just using the y equals mx plus b equation. So this is great then. It means a lot less laboratory work for you. It just means you can figure out whatever you need to know whenever you need to know it. You can also figure out, let's say you want to produce a certain amount, so a certain concentration. You can figure out how much time a reaction has to proceed from this same one then. So you can see, all right, so I need to let it proceed for this amount of time, and then that much will be produced or used up. The other thing about this is if we think of this as just a first order reaction, so A producing B, we can also figure out, okay, so if this much time has gone by and we've produced this much, or we've used up that much A, then here's how much B has been produced. So we can do stoichiometry then to figure out also how much product is produced over a given amount of time for this first order reaction. Here's just another visual of the same thing. It's showing a graph of the natural log of the concentration of A at time. And then as time goes on, we get a nice straight line. So the scientists who would have found this would have just marked, a couple different data points and then drawn a straight line. We can use software to calculate the slope of this, or just the rise over run. The y-intercept would be our initial concentration, and we can find any given point in time what the concentration is. Something else important is that you be able to recognize what type of reaction this is based upon what we're graphing. So the fact that this graph shows the natural log of the concentration of A versus time, and we get a straight line, that shows us that this is a first order reaction. A second order reaction, natural log versus time, is not going to give you a straight line. A zero order reaction for natural log versus time will also not give you a straight line. So if you see something as a graph like this, if you've got the natural log of the concentration versus time, and you get a curved line like that, that would tell you this is not first order. Rather, a first order reaction is always going to look like this. It's going to be a downward slope, and it's going to be a straight line when it's a natural log versus time. If you were to just do a graph of the concentration of A versus time for a first order reaction, it would be that same curve that we talked about before, where it's occurring really, really fast to begin with and then slowing down as time goes on. When we take the natural log, it turns it into a straight line graph. All right, let's practice this using some of the data. So over on the side, the bottom left, we can see our data table. So at time 0, we started with a concentration of 0.020. Time went on all the way to 200 seconds, and we wound up at the end with 0.010 molar of that. So concentration decreased as time went on because A was used up to produce B and 2 Ds. We can see over here a graph that was made with this data. So at time 0, that would have been where we had the 0.020. And then at this point right there, that's where the concentration is now down to 0.010. And the other concentrations just appear somewhere in between. And so a scientist somewhere plotted those points, drew a straight line through it, and wound up with this graph. Okay, I'm going to answer 3 different questions here. So we're going to find the rate law, we're going to find the rate constant, and we're going to find the concentration of A at time 5.0 times 10 to the second seconds. So that would be 500 seconds. Let's shrink this down so we can do the first one. Okay, so A is asking us to find the rate law. And so remember, rate is just, the rate law would be the rate times the equilibrium, or I'm sorry, the rate constant times the concentration of our reactants, and in this case we only have one reactant, raised to the power of its particular order. So we know this is a first order reaction. How do we know this is a first order reaction? Well, look at our graph. We've got the natural log of A versus time, and it gives us a straight line. If we have a straight line for natural log versus time, that means it has to be first order. And if it's first order, that means the order of A, since it's the only reactant, has to be 1. So our rate law is very simple for this. Look at this. We don't have to do any of the factors, figure out, okay, this doubled, this must have doubled as well. We can just look at the graph and say, oh, first order, and plug it in right there. Write it down. So now let's go to our next question. So let's find the rate constant. So the rate constant, that's K. Now remember, K is just the slope for this line. So we can figure out the slope, rise over run, and use that to figure out K for this particular reaction. So before in the past we figured out K by plugging it in with some data, so we used a rate and the concentration and solved for K in the units. But since we don't have rates over here, all we have is time and concentrations, we can't find it that way. But we can find another way. We can just use this graph right here, because remember, the slope of this line right here is the same as our K. So we can in essence find our slope and use that to give us our K. So a slope is just rise over run. We know that from like 6th grade science. And what rise over run really is change in y. So the final y minus the initial y divided by the change in x. So the final x minus the initial x. And if we do that in terms of our graph over there, okay, it's going to be, so can't use the data straight from the graph or from the chart, because this data right here is just the concentration and we need the natural log concentrations. So when we do our rise, we need to make sure that we take the natural log of these concentrations when we subtract them. So what that means is I'm going to do from 0 to 500 seconds, or to 50 seconds. And that means I'm going to find the slope as the natural log of 0.017 molar minus natural log of our initial, which was 0.020 molar. And then divide that by the change in x, which would be the change in time, and that is going to be 5.0 times 10 to the first seconds. What that's going to get for us then is the slope. But let's compare this to another equation, and the equation we're going to compare it to is the first order reaction solved for the first order integrated rate law solved for K. So if we solve that one for K, we're going to see it is the natural log of A at a time minus the natural log of the concentration of A initially, all divided by time. And since the K is negative, that means we would take the negative of this side to get them to be balanced out. So just moving that negative over. So we can look at these two then. Here is the integrated first order reaction rate law, solve for K. Here is the slope equation. And what you're going to notice is these two match exactly. That's why K winds up being the slope, because it's just rise over the run. One thing though, the slope when you solve it, okay, when you solve it like this, you're going to wind up getting a negative number. But the slope, or the K, is just the negative of your slope. And so in order to turn this number into K, because when we solve this, we're going to get negative 3.3 times 10 to the negative third. Since it is the negative of the slope to get our K, we just take that little negative right there and turn it into a positive. Okay, and that just rearranges it. So now we have solved for our K. What are the units on this K? K, we need to cancel out. So when we subtract molar from molar, natural logs, really two natural logs subtracted from each other is the same thing as saying natural log divided by natural log. So we'll just wave our hands and make those molarities disappear. Since they're divided, they'll cancel each other out. All that we're left with then is seconds on the bottom. So that means the units of our K, in this case, is negative s to the negative 1. So that right there is our K value, got by using the rearranged integrated rate law, also known as the slope equation. And just like all other constants, that constant is constant, which means it stays the same throughout this entire reaction. So let's go ahead and record it up top here. And we can use that value for any time in this reaction if we wanted to figure anything out, because it's a constant, so it stays the same as long as the temperature doesn't change and as long as kind of our reaction parameters don't change. So now on to part C. Part C wants us to find the concentration of A at time 5.0 times 10 to the second seconds. So that's after 500 seconds. Now, I know what you're saying. You're looking at this data table, you're looking at this graph and saying, Mr. Jones, this is impossible. We can't find the concentration of A at 500 seconds because the data table stops at 200 seconds and the graph stops right there. That is not true. Now that we know the rate constant Now that we know the integrated first order reaction rate law, we can calculate the rate at any given point. So we can use RK, we can use the integrated rate law, and we can calculate what the concentration is, what the final concentration is after 500 seconds. You don't need to do another experiment, we just need to do an equation. So moral of the story is nothing is impossible when you use science. So we're going to take the natural log of the concentration of A at time t, and we're going to rearrange it so we solve for that guy now. And so the natural log of the concentration of A equal the negative k times the time plus the natural log of the initial concentration of A. So when we plug in our numbers to that, let's go ahead and do that. N A T equals negative 3.3 times 10 to the negative third seconds inverse times the time, which is 500 seconds. I'm just going to go ahead and put that out that way so I don't run out of room. And we're going to be adding that, so plus the natural log of the initial concentration, which was 0.020. Alright, so we've got our information here. We can solve this, but our answer is still in natural log and we want to get it by itself. So we're just solving for the concentration, not the natural log of the concentration. So to get that isolated, to get that canceled out, we're going to have to take this side and put it to the anti-natural log. So the anti-log will cancel out the log, but if we do it to that side, we need to do it to this side as well. So that means we need to take all of this stuff and get the anti-natural log of that. So we type it in, and we should get on our calculators the concentration of A at time t at 500 seconds to be 3.8 times 10 to the negative third. So pretty low concentration. And what are the units on this? Well, let's cancel things out and see what we wind up with. We have seconds inverse, and we have seconds, and so those guys are going to cancel each other out. And then we have that 0.20, and whoops, I didn't put units on it, but the units are molarity, and they don't have anything to cancel them out. So they're going to stay, which means our units wind up being molarity. And that's a good thing, because concentration is molarity, so the fact that we wound up with molarity as our final unit, as the units at left, that means we probably did something right. And we did. So now we know what the concentration is of A, or what it will be, after 500 seconds have passed. Don't need to carry on another experiment. Don't even need to let this one go all the way to 500 to figure out what it is. We can figure out what it's going to be at any given point in time. We can figure out how long it's going to take this reaction to come to completion, because at that time the concentration would be 0. So we can always solve for the concentration at any given point in time.